Here are the notes for Geometry Section 4.5, Proving Triangles with ASA and AAS. So recall from the previous two sections, we have three triangle congruence postulates and theorems. The first one is SSS, and the information we'll need if it has three sides. If it said maybe a side angle side, that's two sides and the included angle pair. Or possibly we had the third one, which was hypotenuse leg, and we use this one. This is only good for right triangles. And note in all three of these, we need to know at least two pairs of sides. Two pairs of sides, hypotenuse and leg. And this one, not just two, but all three pairs of sides. So today we're going to focus on finding triangles congruent if we have only one pair of sides. So how can we do? What are some ways to do that? So we have more angle information. The first is called the angle side angle postulate, and that says if two triangles have two angle pairs that are congruent, and the included side pair is congruent, then the triangles are congruent. So note, this is, now we've got our first round where we can use two angles and one side. Specifically, we need the included side. Included side here is in the same sense as included angle. So we're looking for the side that is formed by or is just between the two angles. So we have some examples of that in our little diagram here. So using this diagram, we'll identify the included sides. For angle ABC, and angle ACB, the included side is the side formed by connecting the two vertices. So in this case, the included side is BC. ADB, ABD, our included side is clearly BD. Note there are two typos on the note sheet here. BDC is a straight angle. I'm unsure is what I was trying to say there. I think I was trying to say ADC. So ADC and ACB sides DC. Angle BCA, and I shouldn't have said angle A, I meant to say angle DAC. Between this angle and this angle, our included side is segment AC. We're looking for the sides that are connecting. Okay, so we'll do a little identification here to figure out like what we should use. Note in these two triangles I have a pair of angles, a second pair of angles, and the side connecting those two. Therefore, this is a classic example of angle, side, angle. In this case, I have a pair of sides, pair of angles, and hopefully by now we're noting the shared reflexive side, angle, and a side. Finally, note that we have one pair, two pairs, and a shared reflexive side, three sides, side. Okay, the other triangle congruence idea is the angle side. This one will be a theorem, so we'll actually prove this in just a second here. The angle side is very similar to angle side angle in that it says that if for two angles, if two triangles have two angle pairs that are congruent, sorry about that, and the included side I'm screwing this up. And the non-included side pair is congruent. Then the triangles are congruent. This differs in this non-included. So what that means is, so instead of having the side between the two angles, we want a side that's not between the two angles. So let's prove this thing. We'll call it good for today. So here's an example to prove this thing. So I'm going to tell you one angle pair congruent, A and D. C and F are congruent, and I know that BC and EF are congruent. Note I have two angle pairs and the side that's not connecting them, so it's not this larger side. But I want to explain why this triangle is congruent. So let's see. So I want to get that my triangle ABC is congruent to triangle DEF. I could use side, side, side. I could use side, angle, side. Hypotenuse, leg, or I could use angle, side, angle. Well, clearly I have two angles and a side. That means I don't have enough information for that, or that, or that. I'm going to have to use angle, side, angle. So the whole trick of this thing is I want to figure out why angle B turns to angle E. Well, since angle A congruent to angle D and angle C congruent to angle F, then by the third angles theorem, the third pair is congruent. So angle B congruent to angle E. There's my angle, my first angle. So I'm allowed to actually claim this with a third angle theorem. I'm given the BC congruent to EF. And I'm also given that angle C is congruent to angle F. So with these three things, I can show that the triangles are congruent. And again, it hinges on the third angle theorem. Since we know two of the angles, you always can find the third because the sum of the angles of a triangle always adds to 180. So you can, as an exercise, you can go through and rewrite this as your own in sentences. But here's kind of the flow diagram as to what this proof would look like. And those were